Data consistency in microservices architecture presents a critical challenge for software architects and senior developers working with distributed systems. Unlike monolithic applications relying on a single database with ACID transactions, microservices manage their own decentralized data. This distribution eliminates the central database and single unit of work, introducing complexities in maintaining data integrity across multiple services. In distributed systems, eventual consistency allows temporary inconsistencies, ensuring data converges to the same state eventually. This approach uses the base model, prioritizing high availability over immediate consistency, a departure from traditional ACID properties. Business logic often spans multiple local transactions, making traditional distributed transactions like two-phase commit or 2PC unviable. 2PC suffers from blocking, single points of failure, and difficulty handling network partitions, which are common in microservices. Concurrent updates from different services can lead to lost updates or other data conflicts, further complicating consistency. Synchronizing data across different microservices is challenging, especially when services need to react to changes in data held by others. Managing changes to data schemas and ensuring backward compatibility across different service versions also presents significant hurdles. To address these challenges, several strategies can be employed, with the SAGA pattern being a prominent solution. The SAGA pattern maintains data consistency without using distributed transactions, breaking down complex operations into a sequence of local transactions. Each local transaction updates data within a single service using ACID properties, ensuring atomicity at the service level. If a local transaction fails, the SAGA executes a series of compensating transactions to undo changes made by preceding successful steps. Other strategies include embracing eventual consistency, using event sourcing, and separating read and write operations with CQRS. Implementing idempotency ensures repeated operations have the same effect, while observability helps detect inconsistencies early. The SAGA pattern can be implemented in two primary ways: orchestration and choreography. In an orchestration-based SAGA, a central orchestrator manages the sequence of steps, sending commands to participating services. The orchestrator waits for responses before proceeding, and if a step fails, it triggers compensating actions in reverse order. Orchestration offers easier monitoring and debugging due to its central point of control, making it suitable for complex workflows. However, it introduces higher coupling between the orchestrator and services, and changes can have cascading effects. Conversely, in a choreography-based SAGA, services communicate through domain events, each responsible for its own behavior. Each service publishes events that trigger local transactions in other services, fostering a more decentralized coordination. Choreography provides looser coupling and greater flexibility, allowing services to evolve and change independently. Debugging can be more difficult due to its decentralized nature, and error handling is distributed among individual services. The choice between orchestration and choreography depends on the specific needs of the project and the complexity of the business process. Orchestration is better suited for complex workflows requiring a high degree of coordination, often seen in brownfield microservice development. Choreography is a good choice for simpler workflows that allow for more emergent behavior, ideal for greenfield microservice development. Key considerations include assessing the complexity, team autonomy, operational maturity, and failure handling needs. By carefully considering these factors and implementing appropriate strategies, architects and developers can effectively manage data consistency in microservices-based distributed systems.